I'm going to redo the question anyway, so it's fine. Okay, that's what we got like that. Let's do it again in phasor domain. It'll make more sense. So converting this to phasors, we do, this is 1 over j omega c. So 1 over j omega c. And then, again, it's the same process, right, as before. So we just label that as our V1, right? I know all this is a ground node, right? So it's a virtual ground there. And again, all the current goes this way is the same as the current going this way. So, yeah, I can just do that. There we go. So what's the current this way is, again, it's just V1 minus 0 over R. And that's equal to current going this way, which is 0 minus VO over 1 over j omega c. And I can just solve for VO now. So that's going to be, yeah, so it's going to be V1 over j omega CR equals negative VO, negative to the other side. And then V1 is a cosine, so it's 10 to an angle 0 degrees. Right? So minus 10 to an angle 0, yeah. Cosine, yeah. 10 to an angle 0 is just 10 plus 0j. And then that's over j, or I'll say 0 plus j. And then omega CR. Omega is 7 times c is 0.5 times 10 to the negative 6 times r is 150 times 10 to the 3. So that's equal to negative 10 plus 0j over 0 plus, and now this is 7 times 0.5 times 10 to the negative 6 times 150 times 10 to the 3. So 0.525j equals VO. Now I think my calculator will be able to do this without having an issue. Negative 10 over 0.525 and so I get, yeah, I get a positive number for some reason. But if I took away the negative there, I get a negative number. Interesting. This 0? Oh, which 0? This 0? Well, that's just 0 plus. So I'm just saying essentially, because I want to write it as a plus bi, bj, right? So I'm just writing 0. There's no real part in the denominator. 7. Yeah. And same thing here. I'm writing 0j just so that it's against a standard form of a complex number. Right? Yeah. Like, yeah. Right. But interestingly, I'm getting not the wrong number, but also not the right number, which is a little strange. So I'm getting 19. Oh, no. I think I understand. Yeah. 19.05j, which is 19.05 to an angle of 90 degrees. And let me just see in here quickly. Let me look at the negative theta. 0 minus 0. Is that the same thing as what they got? I can't tell. They got negative 19.05 sine of 7t. So that would be negative, do this in a different color because it's the answer from the book, or answer from the solutions, which is negative 19.05 cosine 7t plus 90, which is negative 19.05 to an angle of 90. Or maybe it's minus 90. Yeah, you subtract 90. So angle of minus 90. Is that the same thing? Yes, that is the same thing. Never mind. So a vector of length 19.05, negative 90 degrees is, but like, so the direction it's facing is, you measure from here. So the angle here is negative 90. It's 90 down. But then the actual magnitude is negative as well, so it points up instead of down. So yeah, that's your 90 degrees or negative 90 degree rotation, right? That is that's what I get. Right. Yeah, but there's no real number, right? It's zero plus, so it's just straight up, right? Of length 19.0. Okay, so this is the same answer that they got. They just didn't write it properly. And they actually did it in time domain, and they got the right answer. Why did I get the right answer? Why did I not get the right answer here? I did the integral of 10 over. I did the same integral, and 10 over 7, 150k, 0.5. Yeah, I did the same integral, and I just got a different number. Why did that happen? I did exactly the same steps here. 10 over 7 times 150. Oh, times 0.5. I just forgot about the times 0.5. Times 10 to the negative 3. And I get 19 point. Okay, good. Yeah. We do get the same answer. I forgot times 0.5, and now you get 19.05. And now you get the same answer. So, time domain, phasor domain. Okay. Yeah. Negative 90, because you got to switch from a sine to a cos, you got a minus 90 there, subtract 90. Yeah. It's really confuses me a lot too. I can never remember if it's add 90, subtract. Don't even try to, like, I can't even figure out how to go from cos to sine. Obviously I could figure out if I had like Desmos in front of me and I really thought about it, but yeah, this second, can't figure it out. Okay, well, I got a call because it's 6:30 now, so I'm gonna make a quick 5-minute call, talk about tutoring a little bit, and then I will be back. Sounds good? Okay, so I'll be back soon. Yeah, about the cosine. Yeah, for sure. Yeah, it's not the same answer. But it won't be the same equation that they got, right? So essentially I'm just doing, like, you can convert this, it's gonna be 12 squared. It's a really weird way to convert it, but you can't do this. So. I'm sure it'll give me the, yeah. I'm sure if I just don't include this, I will get the right answer. But plus phi, I would never ever think of doing that on the test though. On the test like that, right? That's weird. Let me see. Andy, no, and like, yeah, Andy uses this. This what I have in front of me. Yeah, that's why I do this, because that's. But yeah. I think I'm gonna email Andy and see if he can give me an explanation, and then about the exact differences. I think he's maybe mentioned it, but I can't remember. And we are getting different answers here. So, okay, I'll email him and I'll figure that out. Does that sound good? Yeah, Bodhi plot, and we'll do that. Bodhi. Oh, we get the end. Let's try that, and hopefully that'll go well. Let me find what's the thing? There you go. Draw Bodhi plots for the following thing. Did we do this one? We might have done this one. No, never mind. We didn't do this one. 10 j omega over 0.1 j omega plus 1, 0.2 j omega plus 1. Great. And then, so not in standard form, so we got to put in standard form. So j omega, and this is, so 0.1 is the same thing as 1 over 10, right? So it's j omega over 10 plus 1. And this is 0.2 is the same as 1 over 5, so j omega over 5. Yeah. Okay. Now we got to identify all the things. We have, make a list. We have constant gain of 10. We have a pole at, no, sorry, a 0 at origin. We have a simple pole with p equal to 10. We have a simple pole with p equal to 5. Okay. So for each of these things, we need to make a phasor and magnitude plot and all that. And magnitude and phase plot. And from there, we'll see. Okay, so this one here, I'll just try to sketch it and see if that works. And if it gets too confusing, I'll do actual plots of them. So sketching it, it's going to have a, this is the magnitude. It's always, I'm not going to label it. It's always magnitude then phase. Magnitude then phase. So magnitude, it has a magnitude of 10. Actually, I'll do that in a different color. I'll put the labels in a different color. So 10, and then the actual plot, it will have a constant magnitude. So there we go. And the phase, oh yeah, you're right. Yeah, I should have my notes open. I won't make mistakes like that. Yeah, you're definitely right. So it's not at 10. It's at 20 log 10 of 10. Right? So 20 log of 10 is 20. So it's at 20. Not just right here. 20 equals 20 log 10 of 10. 20 goes there. Yeah, thank you for that. That's exactly right. Now that I have that, we can continue with the 0 at origin. So the 0 at origin will get a plot like this. Again, if it's too confusing with just my sketches, then we will. But it's really just, it's literally just exactly that, just a line here to here, and the slope is 20 decibels per decade. And I should be clear, the origin is 1, right? The x-axis is, on the x-axis is 1. Oh, sorry, yeah, it's 1 there too, yeah. And then the phase plot is a constant 90. It's a constant 90. 1. Okay. Yeah. Yeah, that's for the constant gain. Yeah. Yeah, well, remember this axis is 20 log, is always 20 log 10 of the magnitude of the transfer function. And so if we just take each bit individually, right? Okay, then I'm doing 20 log 10 of just 10, right? And so then that's 20 for this example for 10. But yeah, so that axis is always the 20 log 10 axis. sorry, not that axis, sorry, this axis. This is the phase. But this is the 20 log base 10 of h of omega, the magnitude. Yeah, even here, that's also the same thing. It's also 20 log 10. And we do it like that because that lets us sketch it like this. That lets the sketches happen, and like it lets us like be able to break things apart and then add the graphs together. So yeah. Okay. So then continuing on, I have a simple pole with p equal to 10. Okay, so again, magnitude, then phase. So simple poles look like this. It's 0. We do a little bit of a cleaner sketch. It's 0 until the pole. So the pole was where? It was at 10, right? So it's 0 until 10. Until 10. And then from 10, you go down with a slope of negative 20 decibels. And the phase plot is a little bit more complicated. So the phase plot is a little bit cleaner, there we go, is 0 until 0.1 of your pole. So 0.1 times 10 is 1. So 0 until 1. Then at 1, that's it. 0.1 P1. So that's 0.1 times 10, which is 1. There. So it should be clear. I'm going to say P1 equals 10. And then from there, you go down. Yes, this is where this is 10. You go down until here, should be negative 45 degrees. And then after that, you go until 10 P1, so you go until 100. So that's 10 times P1, that's P1, and that's 0.1 P1. This is always how it's going to work. This is for the specific example that P1 is 10. And then here, once we reach here, this should be negative 90 degrees, and this should be a flat line again. Okay, so there's our phase plot. And now our simple pole. Really struggle with straight lines for some reason. There we go. That's nice. I swear when I'm teaching, I use these tools, but I guess I should now. I don't know why I don't. I'm just lazy. P2 equals 5. Pull it 5. Okay, so it's the same idea. We go until 0.1 times 5, which is 0.5. So that would be, if this is 0.1, 0.5 would be like right there somewhere. I don't know, right there. Okay. So again, that is 0.5 because that is 0.1 P2. Okay, then we know that at 5, yeah. Okay, magnitude first. We go until P1, P2 I mean, which is 5. And then from then on, you have a negative 20 decibel decade. Did I label all my slopes? I didn't. The slope has to be labeled too. Negative 45 degrees, decibels, sorry. No, degrees, sorry, per decade. Mm-hmm. The phase? Yeah. P is in the numerator. P over 10. Oh, yeah, but it's the thing in the 0.1 P1 is the same thing as P1 over 10. And so that's why I have my turning point at 1. Remember the origin. Yeah, so 0.1 P1. P1 is 10 in that case. P1 is 10 for that pole. And so that's 1. And now that's 10, and that's 100. All right, there's that. Yeah. But because like on the axis, right? At negative infinity on the line, that's where 0 is. That's infinity, right? Because that's 100, 10, 1, 0.1, 0.01, right? So 1 is at the origin, quote unquote origin. It's not the origin, but it's where the x and y axis cross. That's 1. That's 1. Okay. So yeah. Then we have that. Good. Magnitude's done. Then again here we go until 0.5, which is approximately there. Right? So that's 0.5. And then we go negative 45 decibels per decade at 5. So it's like here. We should have 45 degrees, negative 45 degrees. And then at 50, let's just say it's right here. We should have negative 90 degrees. Okay. And so the slope is negative 45 degrees per decade. Okay, and then we add all the plots together. I'll do that on actual plot paper. Yeah. Mm-hmm. This one or this one? Okay. It's 0.1 P1 at the origin. 0.1 P1. And it because P1 is 10. So it's 1 at the origin. It's always 1 on the omega axis. It's 1 at the origin, 0 is all the way down here, and infinity is all the way over here. Right? But it's always in general, it's always 0.1, like the breaking point is at 0.1 P1, which happens to be 1 in this case because P1's 10. And then the middle point is at P1, the other breaking point is at 10 P1. Right. Yeah, no. There's no. Yeah, and then you just do it twice, and then you're gonna end up with them. Yeah. Okay, so magnitude plot. I'll make it big so that I can actually really see what's going on here. So I'm just gonna dot the origin just so we can see it. So there's our origin, and I'll add all the magnitudes. So essentially, to add the gain, that just means you start at 20, right? You start at 20 here. So it's gonna be like we have 20 coming in. But I guess first let's show our breaking points. So from 0 up until 10, I think. Oh, I didn't label this. Where's that breaking point? It's at 5. Okay, so 5 actually. 5. So that's the first zone. 5, 0, 5, 5. Okay. That's at 5. Oops. That's at 5. 5. That's at 5. That's at 5. Then from 5 to 10. Right? 5 to 10. 5 to 10. 10. Yep. 10. 10. 10. 10. And then finally from 10 on. Just for the magnitude plots. And so I break it into 3 sections because I have 2 breaking points. Breaking point there and a breaking point there. These ones don't have breaking points. So then I can do this by just adding everything up. So it's going to be essentially 20, but with a slope of 20. That's weird. What do I do? So I do a slope of 20. Yeah, but I think Yeah. Okay, so this is what it is. So it's a slope of 20, but my intercept is at 20. So then that should be like this. It should look like this up there. So what I did is I looked at this. I said, okay, well, our slope is definitely 20, right? There's no other slopes from in the green section, just in the green section, right? There's no other slopes. These ones don't matter at all. They're 0. So it's 20, but it's not going to look like this. Okay. It's not going to look like this, going through like that, because we have a constant gain of 20. So I should just bring that up by 20. So essentially, to deal with the constant gain is just at the start, for the first one, just bring it up by whatever amount, or bring it down if it's a negative constant gain. So just bring it up or down. Well, it won't be negative. Sorry. Yeah. So just like that, then you have that. So there you go. So that's the first stretch there. So I will draw that in the line. It's 20. It's 20. The slope is 20. Yeah. Right? Because you see here, our slope is 20. Like that. And the slopes are just 20, but you have to constant gain bring everything up by 20 points. Everything up by 20 points. Right? See, it doesn't go through the origin. It goes through 20. 120. Then for the next section, the yellow section, we have so I can forget about the constant gain now. As long as I just continue from this where this left off, the constant gain's accounted for. So I can completely forget about it now. Just add the slopes. So the slope in the yellow section is 20 minus 20 minus 20. So it's negative 20 per decade, and that goes. Oh, sorry, that doesn't go to 1, does it? Sorry, it goes to 5. I'm supposed to go to 5. Okay, so you see, I'm supposed to go to 5. So where's 5? Let's see. 5 would be 1, 2, 3, 4, 5. So that's where 5 is. That's where our breaking point is. Right, so I'm just gonna label. Maybe I'll label it. Just like there's our breaking point, and there's another breaking point. Right. So this red line should continue until there, but I have to know when to stop it. So the next point on the line would be right there, right? So I can continue my plot like that, right? But I have to. That's a really bad plot. I have to stop the line at 5. Okay, so if I had a plot that went like, sketch it. There you go. I have to stop it there. So that's essentially how I do that, right? Because the line wants to continue to 40 at the next decade, but I have to stop it at 5. So there we go. I stop it at 5. Okay, then from 5 to 10, it's a slope of negative 20 decibels per decade. So I'm just going to figure out, okay, in 1 decade, I would be at 50, right? So 20, 30, 40, 50. 20, 30, 40, 50. So that's that line. And in 1 decade, I go down by 20 decibels, so just eyeballing it, it'd be right there, right? So that would be that line. But I need to stop it at 10. I can't let it go that far because I have a breaking point there. So it ends there. So that would be the next point. And then from 10 onwards, we have 20, negative 20, negative 20 again. No, sorry. That's... Whoops. Made a mistake. The yellow section has slopes. So that's wrong, what I just said. The slope was wrong. Let's go back to the yellow section. Forget about constant gain. I have a slope of 20, no slope. Slope of negative 20. So it's just 0. The slope is 0. Now, in the purple section. Yep, so the constant gain is already accounted for. Just from the first bit there, from the first fact that I brought this up by 20. Now, if you think about it, the whole graph is up by 20, right? If I just continue where I left off, if I just continue drawing from the last point, the whole graph is up by 20. So I can forget about it. No. You just apply it the first time and then just continue drawing from where you left off. And then the constant gain will be applied. Yeah. So the slope here is 20 in the yellow section. We're talking about the yellow section, right? 20, 0, negative 20. So it cancels out to 0 there. Slope of 0. And then now in the purple section, 20, negative 20, negative 20. So now it'll have a slope of negative 20 decibels per decade. So the next point would be right there, right? Next point would be right there, and it would continue like that. Oh boy. I'll just use the line tool. The line tool is really weird in OneNote. That's why I don't use it that often, because it's like, see how it's like, it sticks to a grid? Can I turn that off, actually? Options. I have, like, we are technically responsible to know how to deal with the quadratic poles, but I have a feeling, he didn't outright say it, but I have a feeling it's not going to be a quadratic pole one. Just by the way he was discussing it, he just sort of like, he mentioned it, he talked about it a little bit, he drew the graphs for it, but he didn't do the whole derivation for it, and he said it was less important, and it was just like, he didn't completely outright say, no, this will not be on the test, but I feel like just because he can't say that, I think fairly confidently there will not be a quadratic pole on it. Yeah. If it was JW plus 1 in brackets, simple 0. That would be a simple 0. Zeros are all on the numerator, poles are on the denominator. The reason for that is because, right, like the factors here, like, would make the whole thing go to 0. Right? The whole thing, if you had a 0 up here, the whole transfer function would go to 0, right? Because you're multiplying by 0. But if you had a 0 down here, you'd have an asymptote, because you can't have 0 at the denominator, so it would infinitely increase. So you literally have like a pole going up in the transfer function, right? The transfer function, if you try to actually graph the transfer function, it's a complex, like a complex analysis graph, right? So that's what it looks like. That's the transfer function that we're graphing, and so literally, like, you see, well, show these. It's an interesting video if you want to watch it. Literally, like, that's a pole. Like, a pole is like, what we're talking about, a pole is right there, and a 0 is like there, or whatever. I don't know, some zone here. That's fine. No. If you had j omega, and then j omega plus 1, then you just have you'd have a 0 at origin, and then a simple pole with z equal to 1, because this is over 1. It's over 1 there. Right? It's over. So yeah. Okay, there is our magnitude plot. Let's see if that's correct. Yep, they drew the same thing. Going up to, yeah, a little less than 40. Yeah, their plot has the highest value here of 50, so it's a little bit, like, here is our plot. That's where 50 is. So there's a little stretched out, but yeah, it's the same plot. And then I need the phase plot, and yeah, so let's see the phase plot. So the phase plot is wait, sorry, forgot what I was doing. 0, 90. So this essentially gives nothing. This gives a constant gain of 90, right? And then we just have to add these two together. So we can essentially just focus on the last two here. And we just think about the breaking points, right? So we go from 0 to 0.5, no issues there. It's just 0, right? Well, sorry, it's not just 0. It's a constant gain of 90. So it's 90 from 0 to 0.5. Then from 0.5 to 1, we have the yellow section. From 1 to 100, oh, sorry, no, not 1 to 100, sorry, 1 to 50, to 50, like that. From 50 to 100, like that. And then from 100 on, like that. So I'm actually just going to just bring this down, so that I don't have to scroll so much. Okay, so from dot at the origin, From 0 to 0.5, no arguments, we have 90. That's it, just 90. So 90 is here to 0 0.5, 0 0.2, 3, 4, 5 is right there. So there we go. There's the beginning of our phase plot. Then after that, we have the yellow section. The yellow section has a slope of 0 and then a slope of negative 45 decibels per decade here. So negative 45 decibels per decade would mean that at, so this is 0.5, so at 5, 1, 2, 3, 4, 5, we should be at negative 45, which is right there. 1, 2, 3, 4, 5. Sorry, I went too far. Because that's 1, 2, 3, 4, 5. We should be at negative 45. So the next section of our slope would look like that, but we have to stop it here. Right? We have to stop it there at 1, because the yellow section goes from 0.5 to 1. Then in the purple section, we have a slope of negative 45 and another slope of negative 45. So it's a slope of negative 90 decibels per decade. So at 10, we should be, so this is like a little less than 90. So this should be a little less than 0 at 10. So right there. That kind of goes like that. But where should it stop? It should stop at 50. So that's fine for now. We can keep going. So 50 is, this is 20, 30, 40, 50. This is 50. We label the breaking points. Here's our breaking points. So from 10 to 100, we should go down to a little less than negative 90. So we should be like right there. Line would continue, but we have to stop at the breaking point, right here. So there. The breaking point. Then after this, we have the pink section, which is from 50 to 100. Here we have still just a slope of negative 45, not a slope of negative 90, but negative 45. So again, that's the breaking point's at 100 there. Okay. And so we have, yeah, I see. Then we have here negative 45, so I'm going to go down. This is 50. I'm going to go to 500, 200, 300, 400, 500. And then down by 45. So this is the 500 bits. It did. It was negative 90 here. And now it's going to be negative 45. So it's going to go to here. There. Which looks like a pretty similar slope, I realize, but that's just my drawing. It's not the same. You see, here we go. 1, 2, well, here. From here to here, you can really see. That's right. So we go like that. That'll be. Yeah, 0.51. And then, no, there's not 1 at 10. Oh yeah, sorry, there's not 1 at 10. It's not that there's 1 at 10, it's just that I can draw per decade, right? So I drew from here to here, and then I drew another decade, but then I had to cut it at 50. And then at 100, I have to cut it again, right? So I have to cut it here. So let me draw that line. 100, I have to cut it again, so it's going to look like that. And then from 100 on, it's just 0, 0, everything, so just no slope. And there's your phase. So here we have a slope. Oh, I'm supposed to label the slopes. Sorry. In the solution, the slopes aren't labeled, but I'll label the slopes anyways. So yeah. Why do I have a slope here? Oh, so yeah, never mind. I know why. 20 decibels per decade. Then from the yellow section, it's just, no, the yellow section is nothing. That's 20 decibels. So this is 0, obviously. And so I don't have to write that. And then this is negative 20 decibels per decade. There you go. And then this is 0. This section is negative 45 decibels. Sorry, negative 45 degrees per decade. This is negative 90 degrees per decade. This section is negative 45 degrees per decade. And then that's 0. There we go. All labeled. So, magnitude and phase. Yep. simple 0 with z equal to 1. Because j omega plus 1 is equal to j omega plus 1. So simple 0 with 1 as your. Okay, and that's pretty much it for today, guys. That's it. We have 3 questions, but that's the midterm, right? So we essentially did the midterm as well as we can. And so I will send an email about this and ask for any clarification about that we can do. Yeah, I know it's because if you look at the plot here in the yellow section, right, just the yellow section here it has a slope of 0, and here has a slope of negative 45. So it has that. But then in the purple section, it's negative 45 and negative 45, which is going to be negative 90. And then the pink section, again, it's just 0 slope here, negative 45 slope here. So I get negative 45 again. And then in the blue section, it's 0 slope, so it's just 0. Make sense? PCS lab. Yeah. Well, it's weird. It's weird. Yeah, I think what you should do is, okay, email the TA, but if the TA doesn't respond, email the professor saying the TA doesn't respond, and then the TA will respond. Right? Yeah. So do it now. Do it soon so that you get the answer as fast as possible. So email the professor. If the TA doesn't respond, just email the professor, and then the TA will respond after. If you want to send me your data and send me your data, I'll take a look at it when I have a minute to sit down. Send it, and then I'll see if I can get it. But I can't guarantee I'll have an answer. Okay, guys. Well, I'm gonna go have dinner. So you guys, hopefully you do too as well, and then